Hello everybody, so today I will talk about how we can design the Ticketmaster. This is a follow-up video. So last time I talked about how I can design Ticketmaster. So I started from the functional requirement until the high-level design with also I talked about the strong consistency. Okay, so now I'd like to talk about 3 more topics. So let me get started with the first one, the array of webhook from payment system. So in my last video, I talked that I can use the third-party payment system like Stripe, and because PCI regulation is so tough, and we don't wanna, save the credit card information in our database. So we use the third-party payment system like Stripe, and so system makes the webhook to our payment webhook service, and in that way we can know that the user made the payment. But there is one thing I'd like to mention about this. Okay, so there is last time I talked that we'd like to secure the ticket for 10 minutes for the kind of grace time for the payment. And the thing is that, so let's say the user finished the payment just before 10 minutes, and then the webhook makes the payment system makes the webhook. So let's say user makes the payment at 9 minutes 59 seconds from the seed is secured, and then webhook is made at 10 minutes 10 seconds. In that case, because 10 minutes have already passed, it is possible that there is another user who secures the seed and who starts the payment. So this is not a good idea. This is not good for the second user. So what I can do to avoid this is we can make the grace period, let's say 10 minutes, and then actually here when we set the secure until, I set something like 10 minutes and 10 seconds. So that's something I can do. Let me think. So 10 minutes. No, it doesn't helpful. It isn't helpful because it just sets the grace time with 10 minutes 10 seconds. So what can I do? Okay, I see. So we set secure until to be 10 minutes and 10 seconds later from the seed is secured, and the third party system makes the webhook. So obviously we need two timestamps. One is 10 minutes where user can make the payment, and 10 minutes and 10 seconds at this moment the seed is now available to other users. Okay, so what I can do here is, I think we need two timestamps here, secured at and secured until. So we accept the user makes the payment if the timestamp is before secured at plus 10 minutes. But this seed is not available for other users until secured until, which is 10 seconds later than secured at. Of course, it is possible that we just have the secured at timestamp, and the log should take a look at only secured. We pretend that the rock is now available. Sorry, what should I say? So we make sure that when booking service makes a query, we search with secured at plus 10 seconds is later than before now, and if it is true, the user is able to secure the state. Yeah, it is possible to include that logic, but rather than that, for simplicity, I use two columns, secured until and secured at, and I make sure the secured until is already secured at plus 10 seconds. So again, I would say user can secure the state if current time is greater than secured until, and user can make the payment if current time is secured at plus 10 minutes or before. Okay, so that's about the webhook delay. Okay. Now I will talk about the scalability. So this is the number I'd like to support. Scalability, 100 million daily users, 100K event per day, 100K spike. So I will do the quick math from here. So, okay. Oh, and actually, I have to take care of two things. So one is request per sec, so throughput. The other is data size. That being said, 100 million daily users is yeah 100K event per day, 100. So the most important thing is how many times user makes the payment, booking. So let's say there are 100 million daily users and 1 out of 10 makes the booking. In that case, 10 million booking per day which is 10 to the 7 times 10 to the 5 to make it seconds, and now no. So in this way, because 1 day is almost 10 to the 5, so 100 bookings per sec. Okay. And let's say each user makes maybe 10 pages of search or maybe viewing the event. I don't distinguish them for now. I just would say each user makes 10 requests per day in that case. Wait, so this should be 8, right? Oh, no, wait, I do this. Okay, so 10 to the 8 daily users, and each user makes 10 requests, so per sec this is 10K view per sec. Okay, and because there is spike, this can be up to 1 million view per sec, and this can be up to 10K booking per sec. So just to be clear, this one is read request, and this one is write request. So obviously write request, the throughput of the database, for example, is lower for write request. Yeah, so that's what I have to take care. And also I have to take care of the data size. But for now, let me start with how I can handle, these requests per sec throughput. So I will go with 1 million views per sec. So here, API gateway, this is good because as I said, this is the cluster of servers, and this I can think API gateway scales out internally. And for server, I will make it scalable with wait a minute. So I will use the auto scaling of, let's say, EC2 instances so that they can horizontally scale. So the good thing is these APIs are stateless, so I can just scale out horizontally. So because typically one EC2 server can handle simple request 10K. So I would say 1 million view. In this case, we need 100 servers. This is realistic number, I think. Good. So this is about the scaling of this event server. And for search event, we have to handle, as I said, 1 million views per sec. So let me start from this event DB. So basically, for PostgreSQL, it can handle around 100. Let me check. Okay, I just took a look. So basically, PostgreSQL can handle 50K requests per sec. So we need read replicas. So there are 20 read replicas. So as I said, we can accept the, what was it? So eventual consistency. So we can use read replica. So there are 20 read replicas. Okay. And for Elasticsearch, I don't have a specific number in my mind, but something I can say is we can, use Redis to cache the result. So for example, and one thing I can say is, even though I told that there is a spike and there should be 1 million views per sec, I'm pretty sure it doesn't come to the search, or it says maybe user makes the search when spike, but the search word is quite similar, like Taylor Swift. Yeah, or the artist performer who just announced the event. So in those cases, Redis works very well. So I would put it in between the event service and Elasticsearch as the read-through cache here. And for Redis, Redis can handle around 100 million. No, 100. Let me check. Okay, so Redis can basically handle something like 100K requests per sec. So this is very, yeah, in the time of spike, we need 1 million view per sec. So maybe if we really need it, I can use the kind of, what is it? So we can use the Redis cluster, but instead of that, what I would do is cache the data inside of event service, maybe like in memory cache, or maybe we boot up the Redis inside of the event service. Ease of the work. So in that way, I put Redis here so that Redis upper limit 100k per request per. Sorry, so we don't have to use the Redis cluster just for the spike time. Okay, so that's about the read request per sec. Now we'll talk about 10k booking per sec. So the request comes this path now. So here, as I can see, I need only one server actually, but thinking of the availability, I think 2 or 3 servers prepared, as this horizontal scaling is a good idea. So I would say I use 3 servers here. And third payment system, yes, they will, do the best. And for payments webhook service, the same. Even though I'm pretty sure one server can handle all of the webhook requests, I would put 3 servers for the availability. And for EventDB, we have to handle the write request, which is 10k booking per sec. But something I have to take care is because we use the locking. Oh, no, because this is the right query. We cannot obviously handle the query with read replicas, but basically PostgreSQL can handle 10k requests per sec for write, so this can work. So yeah, this can handle it. And obviously, because write request comes into the EventDB, maybe what I can do is, obviously we can catch the result of the event and here in the Redis. For event, this is best suited for the caching because event is always the same. We just have to return the same event data to each user. So this Redis cache completely works. Okay. And in case of PostgreSQL, write request is always handled by the primary node. But as I said, primary node can handle around 10k requests per sec, so this is fine. Good, now I could talk about the scalability. So let me talk about the data size quickly. So 100 million data users, 100k event per day. So I will talk about the event and seats because they're, the data size of the booking, seat, and event increases day by day. But for users, the increase of the number is quite steady, I would say. So I will talk about, but maybe I can think of the user number first. I can say the total number should be 10 million, or maybe if this is global, maybe maybe 1 billion users. Yeah, and user data includes something like user ID, name, phone number, maybe 100 bytes. So in total, it should be 100 byte. Billion, so sorry, terabyte. So this can be stored in a single PostgreSQL. Currently PostgreSQL, like Aurora in AWS, can store maybe hundreds of terabytes of data, so this can be stored. And for events, so this is tricky because when I create a 100K event, each event has maybe 10,000 or maybe 50,000 seeds record. This is quite big, so I would talk about the seed records because I'm pretty sure it's much larger than the event records in terms of the size. So let's say each event has 50K seeds, and every day there are 100K event. So in total, how much is it? 5 terabyte. Wait a minute. So what? 50K, 100 bytes. No, so this is the number of seed, and let's say each record has 100 bytes of data. So assuming this, how much is it? So 1 kilo million billion. So, oh wait. So kilo million billion and 5 billion times 100 bytes is 100 terabytes per day. It is possible. 50K seed per event, and each day 100K event per day. I can't believe this is possible. 100K event per day. Yeah, but good. Let me double check. Okay, so yeah, I would handle 500 terabyte per day. So in this case, this is really huge. And I can say okay, so this is about the seed. For the event itself, I don't need this 50K number. So actually, this should be 150 gigabyte per day. So until this reaches 100 terabyte, there are so many days, like two. Okay, so I would say per year, it becomes around 3,000. So 15 terabyte per year. So this can be stored like 10 years until it reaches 100 terabytes. But this is quite huge. Yeah. So what I can do here is, yeah, I will separate the database for seed and bookings. So I would write it. So I create booking DB here and moves this ticket and seed and something like that here. So now booking service takes a look at this. Okay. And even if I do that, this ticket DB is quite huge booking DB becomes quite huge. So I would move this tail data to S3. So I will kind of hand wave the process between this, but I know that AWS supports and provides so many kind of data connection between database and S3, so I can use it. So, and also I can do is maybe if the old data, I can move it to the cold storage. So with the cold storage, it's much cheaper, but it takes time to fetch the data, like maybe 1 second, maybe 2 seconds, 3 seconds. But I think it is fine. This happens when user tries to fetch their kind of history of the ticket. So in that case, user have to fetch the record from S3, or maybe we can store what I can do is here we created the ticket record because we need to do the row rock, but after the event is finished, we don't have to use the row rocking. And typically the use case is that user takes a look at the past his booking ticket records. So the query pattern becomes per user. So maybe we can put the booking, seat or ticket records in the per user. We accumulate or put the ticket records for the same user in the same S3 file, and in that way the fetch becomes much earlier, because when user opens his booking history page, the system just has to pull the single file which stores his bookings records. Okay. So yeah, in that way I can make the PostgreSQL database size realistic. Yeah. So that's what I can do for the data size. Okay. Now I will talk about the final topic, which is the waiting queue. So here I will talk about the problem of this current system. So even though we introduced the ticket securing mechanism, the problem is, let's say Taylor Swift announces a concert. There are 50k seats, and there's so many users coming in to the website, and they try to take and book the seat. In that case, firstly, the seat is shown as available. However, on the next moment, so many users who see the website tries to secure that seat. And what happens is that even though it was shown as bookable, available, when he clicks it, it shows as the unavailable. And then they try to find the next seat, but it's not available in the same way. So in that case, what happens is that even if user comes to the web page first, opens the web page first, because he was unlucky and he misses the first seat, he fails to find it. Yeah, so this is not a good, user experience. So one of the ideas to make it more comfortable for users is introduce the waiting queue. So when there is a waiting queue. So when user clicks the kind of enter, or I should say, choose the seed, he has to wait in the waiting queue. And waiting queue, there is a kind of number of people who can book the seat. Let's say maybe 10,000 users, up to 10,000 users. And what happens is only those users can select the seat and book the seat. Other users has to wait, and when the time has come, he can go into the booking page, and he can book. But he's given only, let's say, 10 minutes for him to choose the seat. So this is the idea of waiting queue. And of course, if there is a user who makes the booking, then the next one person can join the booking page. Enter the booking page. So the kind of slot is available. Slot becomes available if the user in the booking page finish the booking, or he didn't book for 10 minutes. Okay, so this is what I will design from now. So for this waiting queue, what I can do is, of course, we need the waiting queue. So let me get started with that. So I put it here. So when firstly user tries to book, he is pushed into the waiting queue. So this can be the real queue like SQS or Kafka, or maybe we can use the Redis SortedSet. And my preference is using the Redis SortedSet because it has a TTL. So TTL can be used like if there is someone in the waiting queue, Redis SortedSet, and if he doesn't make any action, the record is deleted in 10 minutes with TTL 10 minutes. So that's my current idea. So this is Redis SortedSet and sorted by timestamp, or I should say waiting from timestamp. And TTL, I would set waiting from TS plus 10 minutes. So when user makes a request to book, he is pushed into this sorted set first. I would create a new, server here because this is exactly the server where so many requests comes and it has to handle. So booking entry service. So API gateway handles the request to here, and then booking entry service makes the pushes this user into Redis SortedSet. Okay. Now I have to think of two things. How I can make sure that the user who's in the Redis SortedSet is able to book the seat. Let me see. Wait, so I think we need two things. Number one is we have to track two things. Number one, users who's waiting in the waiting queue. And number two, users who are in the booking page. So, yeah. Okay, so my idea is for the booking page users, I use the Redis SortedSet. But for booking waiting queue users, I use Kafka. So the flow is like this. When user tries to wait in the waiting queue, he is pushed into Kafka. And when he enters the Redis SortedSet, he's pushed into the... When a user enters the booking page, he is stored in the Redis SortedSet. And the problem here is how I can move this to this. So I use the queue handler here. So this is a sorry. This is a kind of cron job, right, which is run every 1 minute. And what it does is counts the number of records in the SortedSet and fetches users waiting in the waiting queue and moves them into this Redis SortedSet. And now what I can do is, if there is a user who'd like to go into the booking page, we need kind of authentication, or I should say authorization, that he can enter the room or not. So here, before we accept the purchase request, the booking service has to check if that user is still in the SortedSet. Okay. So this is how I can handle the waiting queue. I mean, so many users who's waiting for the booking. Okay, so my idea here is, I think we don't have to use the partition for Kafka, because the number of users who can enter the booking page is quite limited, like 10K users. So it's completely handleable for one queue. I know that there's so many users who's waiting in the waiting queue, but it is okay. Or maybe I can partition by the event ID, because they are completely independent. of course, per partition, there should be the consumer. In case of Kafka, so each of them handles it. And for Redis SortedSet, I can use a kind of, prefix, for the Redis SortedSet value. Yeah, so that's something I can do. Okay, and maybe we'd like to show how many users wait, how many minutes he has to wait. So we can do a kind of approximate calculation for this, as long as we know in which position he is waiting in the Kafka. So I think this is possible if we assign the number in the Kafka. Yeah. Or maybe some other idea is we put some number, we put the time. Okay, so the idea is we put the users, we put when users join the queue, when user was pushed into the queue, we store the timestamp in the session token, session data, and also we calculate approximately how fast the queue is moving. Then we can calculate the estimated time he has to wait more. Yeah, and then we can display it in the user's waiting page. Okay, so that's something I can do for the waiting queue system. Okay, I just remembered something I have to do. So this third-party system should make sure that if the user makes the booking, we should delete that user from this Redis SortedSet. Yeah. But I don't think of this to be, I don't persist in, of course it's better that this, oh sorry, it's here. So what I can notice from here is, here now, this payment webhook service throws the right query to DB and also delete the record from Redis SortedSet. But I don't guarantee the atomicity here. I will make this delete as best effort, because even if this delete request fails, the record in the Redis will be deleted in 10 minutes. So I would make this delete as best effort. So this is to lower the implementation cost. We don't want to use the kind of, let's say, transactional outbox pattern here just for this. So, or maybe CDC. I don't want to use CDC for this purpose. So I will make this delete request best effort. Okay, that being said, I finished my today's practice. Thank you so much. Bye.